When we mentioned that June 2019 was warmer than the 30-year annual average in Southern Europe, this sentence is raising many concerns and I would say even many question marks. For example, I put the general question here for, I think many of you will raise, on what 30-year annual average we refer. There are many averages that we can refer here. So what year span is taken into comparison? We mentioned 30-year annual average. For example, in WMO, so in the World Meteorological Organization, there are some technical guidelines in order to use the averages. So for example, we are using 1981 to 2010 average, and also the older one, which is 61 to 1990. But still, this is not giving us any a reasonable amount of information that we want to show to the others. That's the reason why we have an alternative approach, and those are graphs and maps. Maps are actually the easiest part when it comes to visualization of data, and by maps we can show most of the things and most of the variables that we want to present to the audience and also to the readers. And also the very important things are colors and lines, because with graphs and maps, colors and lines, basically we produce our numerical models that we can from which we can derive other data, and also in order to make a weather forecast for the upcoming days, then this alternative approach is much more reliable, and also it's more comprehensible because the mass audience couldn't understand what is cyclone, anticyclone, and those terminology that we mostly use in our field. I will just briefly mention that this is the core of data visualization in meteorology and climatology. So maps, graphs, colors, and lines. And also this is the part where meteorology touches software engineering, especially data science and statistics. So if we move on, I repeated this sentence. I mean, the example that I provided in the previous slide, mentioning that June 2019 was at least 3 to 4 degrees warmer with respect to the 30-year annual mean, but I now mentioned 81 to 2010 in the Northern Balkans. And also I mentioned the region I'm focusing on making an analysis regarding temperature anomaly. But again, for mass audience, this sentence is raising many questions. For example, it is lacking comprehensiveness, because people who are not in touch with meteorology and especially climatology in this part, they cannot easily visualize what does it mean to be 3 to 4 degrees warmer than the annual average, because most of the people don't know even how was it 30 years ago. I mean, most of the people don't know what happened a year before, not to mention 30-year period. But still, it's causing redundancy, and some of these texts are actually replaced with the visuals that you can see on the right hand side of the slide. So with the maps, we have the ability to cover the specific area that we want to analyze. And for example, I mentioned here Northern Balkans. So in R, I made a map depicting the specific area I want to visualize. And also I mentioned that it was 3 to 4 degrees warmer, which I can represent with the color bar. And I mean, on the map, I have a scale at the very bottom of the map. So we have a colder and warmer colors, each of these representing a specific anomaly. So the darker color is the stronger anomaly, and it's easier to comprehend, interpret. Why? But because if we have a dark color, we see that, for example, above Romania, Hungary, Austria, Slovenia, North Croatia, it was much warmer than, for example, in Bosnia and Herzegovina, Montenegro, Albania, Kosovo, Macedonia, and even less slightly above average in the parts of the central Italy down to the Eastern Med. So as you can see, this is much easier. I mean, this is easier to understand than to talk about some specific data in means of text. So I do hope that you could have understood this part. So we will move to the next slide. And yes, I will also mention here that we can visualize whatever we want, providing that our data set has that parameter. For example, on the left-hand side, I have precipitation anomaly expressed in millimeters per day for June 2006, I mean 2006. And on the right-hand side, I have, again, temperature anomaly. More on visualization later. I will even show the code how we can visualize this data. And as you can see, for example, if I want to see the precipitation anomaly across the Northern Balkans, I can see that the green colors are representing weather conditions than average, and the brown shades are representing drier conditions than average. And for example, as we can see in June 2006, we have mostly above average precipitation rate across the Northern Balkans, especially in parts of Serbia, Romania, Bulgaria, Macedonia, parts of Bosnia and Herzegovina, but below average precipitation is registered across Slovenia, Austria, North Croatia, and so on and so forth. These slides that you could have seen in the previous minutes are actually the importance of data visualization in meteorology in order for mass audience and the readers to understand what we have been working on, especially when we write the journals, especially when we write scientific papers, because because it's much easier for everyone to see what we wanted to present. And as we all know, picture is much better when we know how to read from it, especially that's the same thing with the graphs. But let's move on. Again, we are continuing to talk about data visualization importance in meteorology and climatology, but I also mentioned on the first slide that beside graphs and maps and colors, we also need lines, and lines are important, especially in detecting pressure anomalies. And why is that so? Because pressure anomalies are easily depicted by lines. And for example, I have here on the left-hand side of the slide, the European geopotential height for July 29, 2020. So for this year, when we had a massive heat wave. So as you can see, red colors are showing that we have a warm air mass spreading towards Western Mediterranean across the Balkans upwards. So we have a southwesterly track, while the worst of the weather is across the Scandinavia and northern parts of the UK. So this is actually a very important part, because these maps that we are using, as you can see here, are actually very easy to find on the internet. But sometimes the weather models that we already have and the results of the data models and many visualizations that we can use nowadays to predict the weather sometimes will be hard to read, because sometimes we don't agree with the color bar, or the lines are not easily detected, or there is a missing label, especially when we talk about pressure anomalies or pressure by itself. So sometimes even the region we want to specify isn't provided. For example, GFS, the Global Forecast Model, has Italy as a domain under 25 kilometer grid, but I can easily do it in R or any other programming language such as Python. So I can visualize the specific part I'm interested in looking at it. So for example, here I took again the Northern Balkans, so I could have visualized this geopotential height for July 29, 2020 in order to see the intensity of heat wave, and also to see how we stack up with the potential temperatures, and also the weather conditions. Will it be stable? Will it be there some infiltrations from the north and the west, especially when we talk about humidity that can produce some turbulences and also destabilize the, to produce the instability of the atmosphere. Now, we will jump to the numerical models that are actually produced, numerical models that are produced by the national weather centers. So for example, I enlisted here 5 the most known ones and 5 most used by the meteorologists, such as ECMWF, ICON, GFS, UKMO, and GEM. Those are models that are actually available to everyone, so everyone can see the results of these numerical models. But the data collection, and when we talk about data gathering, we gather all of the data with the soundings. I mean, when we talk about soundings, that means that we are lifting in the air the sounding, so it can gather the data regarding the wind, regarding the humidity, and also many of the data comes from the commercial flights. So the commercial flights are really important now because they are tracking the differences between the temperatures and the pressure levels at different levels of the atmosphere. So if we have some turbulences with respect to the temperatures, then we can talk about some instability layer, or even detection of some anomaly. Especially nowadays, we use satellites, ships, buoys, and many other sources to collect the data, such as even automatical meteorological stations. All of those data that we collected are put into some supercomputers. So supercomputers are basically immense computation machine that is hardly to visualize with our own eyes. So supercomputers are basically vast center for computing those data sets. But in meteorology, those data sets are computed through the set of partial differential equations. And why is that so? Well, the partial differential equations lies because, partial differential equations are important here because we're talking about the laws of physics, because atmosphere is a perfect unstable balance. Yeah, it's hardly to even visualize the sentence that I just mentioned, but still, it is very unpredictable, and because we are constantly changing, we have constant changes in the atmosphere, then we have a chaotic nature. So because of the chaotic nature, we have numerical errors. So that means that our forecast will never be 100% sure and 100% correct. When we talk about computing complex sets of partial differential equations, they are based on fluid motion, thermodynamics, chemistry, aerosols, sometimes on the gradient of the wind, and other things that are very, very important in order to get a forecast skill to be on the highest level. But to have a forecast skill very high, we need to have a regional domain. Basically, if we want to specify the weather forecast, for example, just for Bosnia and Herzegovina, then we need to make a forecast model that is covering Bosnia and Herzegovina on horizontal coordinate grid. And also to mention that sometimes if we want to focus on more specific atmospheric analysis, then we need to have at least 34 levels in order to get all necessary data. And that means more precise weather forecast and better forecasting skill. Forecasting skill is also important when we talk about the resolution of the models. The smallest resolution it is, the highest forecast skill, and also we are reducing uncertainty when it comes to the depicting which areas could have a numerical error that can be higher than expected. So forecast skill is basically the measure of accuracy of the model prediction with respect to the observed. For example, in the GFS, you can have, for example, temperature for Sarajevo, it's like 20 degrees, but the reality is 27, 28. And why is that so? Well, because GFS has interpolation of 25 kilometers in the horizontal coordinate grid. So basically, each cell is in the boundary of 25 kilometers. So, for example, if we mentioned Bosnia and Herzegovina, so each part of the Bosnia and Herzegovina is split into 25 kilometers grid, and each cell has been calculated based on the altitude. So on which altitude we are currently. And for example, for Sarajevo, that's around 1,000 meters, which is not true, of course. Why is that so? Well, because we are talking about higher, lower resolution, which is 25 kilometers. And we all know that we are on 500 meters, so we have to correct those data. And for that reason, we use regional domain, which is based on the horizontal coordinate grid, for example, on 5 or 3 kilometers. So we can easily depict even the processes that are not that easy to detect when we talk about on the global scale, because on the global scale, the region is very hard to depict, and that's the reason we need to put more horizontal resolution. So we need to improve the horizontal resolution in order to get more precise data and more precise weather forecast. And that means that we need to have immense computation strength. That means in general, we need to have a supercomputer that will be able to calculate very, very immense amount of data that we collected. And for current weather models, it is already very impressive. We are talking about 5.78 petaflops. So petaflop is around 10 to the power 15 floating points, which is enormously fast. But some weather models in 2025 will reach that speed to be gigantic. That cannot be easily visualized. And for that reason, we should get more precise weather forecasts for the days even above day 5. So after that, we can talk about data formats. We have array-oriented specific data. Why array-specific array-oriented scientific data? I'm sorry. Well, because we are trying to collect all of that data inside of one array. So we have an array for longitude, latitude, for the levels, and also for some models we even have a time, especially when we talk about the reanalysis. If we want to do the reanalysis on the monthly, yearly purpose, or even the daily purpose, then we have some step or time or band. It is actually dependent on the model we use, and also if some model have an ensemble included, which is the new technique for forecasting, then we have the number of ensemble members inside of the model. This one had 1. And as you can see, this is actually the description of netcdf4 file that I put in panoply. So basically, we have some basic information. For example, the name of the variables, dimensions that we are using. So this basically are the dimensions. So for example, if we put the level to be at least 4, then we're talking about tracking the atmospheric processes at the higher altitude. So if we go up with the levels, I think on this model we have 17 levels, being the first one at the very bottom of the atmosphere. We are just raising that. If we raise the level up, then we can get the data on the higher levels of the atmosphere. Oh, of course, we can modify latitudes and longitudes, time steps as well if we're talking about reanalysis on the daily, monthly, and yearly purposes. And also we have units. For example, these are expressed in degrees of Kelvin. So we can convert it into centigrades by deducting with minus 273.15 in order to get the Kelvin. For some models, they're mentioned which target period we can see. For this one is August 2020 to 2021 in April, an initial time when we had initialization of the data. And for example, this is the part that I put on the slide because I will go briefly with the explanation of the code. So basically, I imported some libraries that are already available to our users, put my directory path, and then to import my data set, I wanted to rasterize the already existed one that I downloaded from the National Oceanographic Atmospheric page from North America. So as you can see, this NC domain, I mean NC extension, is basically for netcdf4 file. And we also have a band, and band is 1674. So band was the step, and this was the day that I wanted to visualize. I didn't put here level because I was focused on temperatures. So first I wanted to see how it would look like. So I put the plot, and then I saw that I had the longitude on the latitude on the x-axis and longitude on the y-axis, but I don't want to do that. I want to have in reverse. So I rotated my data set, plotted again, and in the ggplot I put the rasterization parameters such as new data set that I rotated, and also XY to be true, so I can have a spatial coordinates in order to get those tiles. After that, I defined the palette. I mean, I defined the scale with the colors I want to use, and then I imported some libraries in order to get my plot. I use the ggplot because it's one of the most used libraries in the R. So in order to get those tiles, I was using geom_tile, imported my data, and then I mapped latitude and longitude, fill my palette and also my color bar with the parameter I wanted to see. Then I did the rasterization, so I put it in interpolate, so I can see my data much nicer. Then I put some I defined my bar, setting some limits and breaks. Those are just the I would say just for the aesthetics. specified my range for latitude and longitude, specified my theme that I wanted to have, put my title on, and it should look like this. I will now show it to you how it looked like. Let me just share it to you. I don't know if you can see or not, but it should be visible very soon. Okay, this is not enough. It's not here. I will show it to you because I saved it with the map B1 under map B1. I don't know if you can see it. And this is our visualization that I mentioned on the very beginning. So this is the way how we can get the data visualization when we're talking about maps, and also mapping the objects, parameters to the map. Okay. So what I was talking about right now, this data was accessible via NCP NOAA server, and I did the rasterization. So in this particular way, I converted the polygons into series of pixels, dots, and lines. This is how we obtained our final image. To get more specific, after netcdf4 files, we have grip2 visualization, but this time I did grip2 visualization from ICON EU weather model, numerical weather model. So I had an input from ICON, but I did it in Panoply. Why Panoply this time? Well, because grip2 is still not that developed for R and Python. Yes, they are in process of development, but still most of the forecasters are using Panoply in order to visualize grip2 data. So for example, this is the visualization of the precipitation expected in period from June 20 to June 24th, 2020, when we had flooding in northeastern Bosnia. I will play so you can see how it looked like. And as you can see, again, we have a scale that's depicting the colors. So the darker color, the stronger intensity we have. And then we will move to the next part of our presentation. We don't have too much left. So we're not talking about data visualization examples that are very effective, especially effective when we talk about climate change. And why is that so? Well, because climate stripes, as you can see on the right-hand side of the slide, are actually the visual that was produced by Professor Dr. Ed Hawkins at University of Reading. So his idea was to collect the data around the world, put the anomalies that were already calculated, and have just a color bar that can be depicted by the colors. For example, if we have a stronger anomaly, that means that, stronger color, then that means that we have a stronger anomaly, especially in those parts where we end our where we begin and end with our color bar. For example, 10.5 is around like neutral color. It's kind of beige color. So we're matching color scheme to visualize the temperature anomaly with the corresponding year. So that was the idea. And how he did, well, he had a geom tile. He was using geom tile library in order to produce those stripes. And actually, he did for Reading, for the UK, and for the world. But I found the data from National Oceanographic Atmospheric Administration from North America, and I tried to produce the climate stripes for our city. And I'm not sure. Sorry, I'm not sure how clearly you can see it, but here is how it looks. Basically, this graph are showing us the data from 1942 to 2019. So 77 years of data on one graph. And as you can see, we were in the colder period until 1985, 1986. Then gradually it became warmer and warmer. From 2006, we have a significant amount of red colors here, and we're talking about record levels in 2018 and 2019. So basically, we are just proving that climate change is indeed very present in Bosnia and Herzegovina, especially in our town. So that means that our temperature, average annual temperature, is rising and continues to rise. And basically, this climate stripes visualization are used on many conferences regarding climate change and also in meteorology. Moving on to I think this is the very last slide, how we developed our numerical weather prediction system, which is not us. This was the idea of two professors and me. So this was the idea of Professor Vlado Spiridonov, who is the first author of our work, and Professor Mladen Čukić. Vlado Spiridonov is a professor at Atmospheric Department Field at University of Vienna. He was a visiting professor, but from 2020 he is appointed to the position of the University of Skopje, and Professor Mladen Čukić is associate professor at University of Belgrade on geophysics department. What we had an idea is that we want to produce an advanced forecast and diagnostic system for storm detecting intensity, and also to early assess the alert category based on levels. We have 5 levels. So the first one is basically 0, that means no alert. 1, marginal. That means just we have a cloud development, but nothing to worry about. Then slight means that we can have some thunderstorms, but there will not be severe enough to produce the damage. Enhanced as a level 3, that means that we have a level that basically can produce slight damages and also produce the troubles for the infrastructure. Severe, that means excessive amount of rain, hail, flooding, like that was example here. For example, we put here our visualization for July 24, 2020, when Zagreb was hardly affected by the massive thunderstorm. I don't know if you can see, but it was under the 4th category, 4th level out of 5. We don't want to talk about the 5. Of the 5th level, which is extreme level, that means that we can even have tornadoes, but those are rarely depicted on the notas. But the more important part is that we did this forecast early in the morning. So this is the time of initialization. It was 7:48, and it was done in Graz, by the way, in open Graz. So as you can see, we made our forecast at 7:48, and this was the forecast for 20 CET. So it was 18 by Zulu time. In meteorology, we most of the time use UTC or Zulu time. But here we can see that we almost made correct assessment 13 hours in advance, which is a huge improvement. I mean, huge success when it comes to other models. But how our model work is based on VARF model forecast outputs, which is this. So this grid is defined on the regional scale. So this is Southeastern Europe, covering from the northern parts of the Austria down to the southern parts of Greece. And we had a diagnostic algorithm that is based on variable distribution to remove all uncertainties. And initial and boundary conditions are used by GFS model. So we are using existing GFS data. But what we're going to do with the diagnostic algorithm? Well, basically, we put all the criteria according to the literature that we have and all findings regarding the storms and storm systems in the Southeastern Europe. Because of that, we could have produced the algorithm that could get us a high hit rate, I mean, forecasting skill to be very high, but sometimes we could get even higher if we use other models, for example, for initial and boundary conditions such as ICON or even ECMWF that have more forecast skill than GFS. Well, this means that the outputs that we see, we are using the VARF grid, which is 5 kilometers in horizontal. So each of these tiles is basically on 2.5. So it's 25 kilometers depicted by GFS. But the important thing here is that in order to reduce uncertainty of predicting the storm system, in each hour step, because we are doing forecast for each hour, then we will use the maximum criteria that we got from GFS conditions. So in order to reduce that some system could be even diminished by then, and also to remove all those I will say turbulences in the atmosphere in order to get more precise forecasts and to see how the storm system will travel or even traverse across maybe our country, or maybe it will go up or down. This will give us a rough idea of what we can expect from in the next few hours and even hours or even days. Sometimes we do the forecast for 4 or 5 days. Sometimes we just do for 1 day. It depends on the computational strength of our laptops. Professor is currently facing some problems with the laptop, so we're not producing notas outputs right now because even the storm season is almost over, so we don't have we don't have need now to do the forecast. So it happened that the laptop had problems in the perfect time, I would say. But nevertheless, this system was tested even in the tropical conditions, I mean, in the tropical regions, and it detected storms very, very precisely, and also some hurricanes and typhoons. I will just mention that this model will be improved significantly. Right now, there is a plan to develop a web application so people can get notas, notas information, and also maybe we will talk about a mobile application, but that's very early because we already have other projects and also other scientific papers that we want to focus on. I mean, this group of authors, but still, I think that we made a huge breakthrough with this application because it is already taking attention of many users across the world, especially because professor is distributing these materials and these visuals to other colleagues, I mean, other meteorologists. So most of the recensions that we received and critics are positive. So we do hope we will continue uh, with the development, how we want to do that. We will see, but we do hope that we will continue to do it very good. And the last part is Open Grads. I will just briefly mention how we can visualize data. I will not show the example. It's actually a software tool that is widely used for visualizing the data. Some other tools that are also used is ArcGIS. So basically, if we have a geographical data, then some people can use GIS. NCL is a perfect language, but the problem is those tutorials are not easy to find or even hardly to find on the web page. Then we have a Panoply. Panoply is the example that I already showed to you. It was with the precipitation in June 2020 and etc. But NCL is one of the languages definitely I would like to learn, but most of these visuals can be produced easily in R and Python. So R and Python are very powerful, especially for data visualization and also for some statistics. And that's actually the prime role of R, statistical data analysis, which I found very helpful. And also when it comes to data visualization that I'm currently using.